So finally today, before there are no lectures next week, I will introduce this category of diamonds. And so I was already giving a rough outline of what they should be last time. And so let me again explain the idea before going into the technical definition. So there should be some functor which goes from some kind of adic space over QP. So for example, rigid spaces to diamonds. And this should certainly not be fully faithful, but instead it should somehow forget the structure from morphism to QP. And so I think I stated last time that if your adic space was perfectoid, for perfectoid space X over QP, or for perfectoid spaces over QP, the functor which sends X to its tilde has this property. And so then what? And so you already have this functor on some big subcategory here, and then in general you try to interpolate from there. So in some sense you have only one choice what you should do in general. So in general, if X is an adic space over QP, then I stated last time that
this is adic in the possibly non-honest sense.
This is adic in the possibly non-honest sense, but we probably won't really use this in this generality. But there would really be such a functor from general adic spaces over QP to diamonds in the end. Proital locally perfectoid. And so what you can do is you can write X as some kind of so you can cover it by some X tilde, and then there's some equivalence relation. X double tilde, I don't know. Which you need to impose on this Proital covering to get back X. So where X tilde to X is a Proital perfectoid cover. And X tilde over the fiber product as well.
I'm sorry, we should know why X destroyed how local is it?
No, there's only motivation so far. I mean, I will prove this later that this is true. I mean, what I will recall Comes's proofs that if you have general Banach algebra over QPs, then you can find some direct limit of finite total algebras over whose completion is perfect. And so it's clear what the functor is. X maps to the co-equalizer now, the tilde of this diagram. The only question is in which category this lives. And maybe it's also not upper clear that this should be well independent of which presentation you choose here and so on. And so whatever this is a Proital now under the perfectoid space X tilde flat characteristic P. And so an example for this procedure would be so what would you do to just appoint QP? So this can be covered by the cyclotomic extension. And so you send this to the Helix spectrum of QP cyclotomic tilted. QP cyclotomic. Modulo the action of the Variman-Galois group, which is CP cross.
I'm a little confused about the pro-tau locally. So in your definition, the pro-tau site, didn't you have some assumption that it sort of would be embedded into something that was then finite tau? Or is that
I didn't define what I mean by pro-tau now, but I will
Okay.
just do it in a second.
Oh, great.
Okay, so far for the motivation. Now let's do this. And so the first thing I want to make precise is what I mean by pro-tau morphism, at least the pro-tau morphism of perfectoid spaces. So in some sense, all Helix spaces that I will consider from now on, I only look at them from the perspective of a perfectoid space mapping to it. And so I can reduce all my definitions to perfectoid spaces. Morphism f from x to y. Pro-tau. If it's locally on source and target, of the form awesome finite maps by A infinity plus to spa AA plus. Where first of all A and A infinity are perfectoid. So as I said, there's this unresolved issue that in general in a finite subset in a perfectoid space, it's not known that these are necessarily perfectoid. And you can get this A infinity as some kind of completed direct limit of things which are étale over A. So completed is a filtered direct limit, co-limit of AI plus AI plus the ARs and IR again seem to be perfectoid. Such that all the morphisms at finite level, so these are still supposed to live over, they're still supposed to be algebras over this guy. This map is étale. And so this allows more general stuff than I was relying on my paper on Pierre Descartes theory. But I was assuming that these become eventually finite étale, but this condition seems to be of no relevance for what I'm doing now, so I'm leaving it out.
Those fiber products are perfectoid, yeah? Down there.
That fiber product is perfectoid. That's actually true. So I wouldn't have to cover it actually.
The as well refers to that being pro-étale.
The fiber product is, well, this fiber product would already be, so I could take this x tilde equal to this because this is already a perfectoid space.
But you want it to be in the condition that he didn't resonate.
No. The definition X and Y are both perfectoid.
Yeah, but I mean, in this case here, really, I'm cheating. So I didn't say when this morphism is Poitale. It's just motivation and the weird stuff. No.
So is this morphism still going to be open if you don't put any finite?
No, it's not open.
Okay.
The issue is that you can have some perfectoid space might be something like a profinite set, and then you might have smaller and smaller open subsets in there, which eventually shrink down to a point. So this would be Proital in this sense. Like if you look at my paper with Bucket Flood, we define Proital maps of schemes, and those are also not open in general. And this is much more close. I mean, this is very close to the notion that appears in the paper with Bucket. And actually, it's
Wait, so the map from the residue field to the thing is the Proital map?
so if your y is a profinite set over some geometric point, and this x is a geometric point of it, then this is a Proital map, because you can write as the intersection of all open neighborhoods. And each of those open neighborhoods gives you something at all, and then you take the intersection. Okay, so let's analyze what happens in the affinoid case. So if you have two such guys, so let's say have spar A infinity plus over spar A plus, and then some other spar B infinity plus, where this is a completed direct limit. And the same for the B infinity. Where this is over some index category I, and this is over some possibly different index category J. And the situation is as in the definition. So all algebras appearing are perfectoid, and from the maps from these finite guys down there, they are tau. So as in definition. Then we can actually compute what homomorphisms between those two guys are. So homomorphism from here to here, which compute with the structure morphism. So homomorphisms over spar A plus from and they are just objects of pro systems, homomorphisms of pro objects. So in other words, it's the same thing as, and I'm hoping I get the indexing right, the inverse limit over J plus the direct limit over I of homomorphisms over the base from spar A. Okay.
Is it correct that the plus part really plays no role here? I think it's just
It's corrected. Well, so I could state this if it makes, well, if on affinoids I could make the same definition without the plus things, and then the same would be true without the plus things. And it's easy to deduce the thing with the plus things from the thing without the plus things. But the morphism sets are not literally the same. You just have to put this extra condition that one plus thing is mapped into the other.
in your definition of the tau, I just looked at
In my definition of Vital, yes.
is the animal closure of A plus?
Yes. So actually the plus thing is determined. It's determined on the base. Yeah. So you're right. Yes, home spaces are the same. Okay. Okay. So. So this is really representing the inverse, the spar B infinity plus is really the inverse limit in the category of perfectoid spaces. So any map to a perfectoid algebra from this direct limit will automatically extend to the completion because of uniformity of the algebras. And so this is a direct limit of things for overall J, and so is the right-hand side, and so we can reduce to a single. So J is just a point, and so we write BB plus. And that's now tall over the base. And also, so let me write what we have not to check. That the homomorphisms, all homomorphisms are over the base. I'm not writing it. Spar infinity. They are just a direct limit over I. Of the homomorphisms at finite level. So in other words, the spar BB plus is supposed to be some kind of locally finitely presented functor. And so this can be checked locally on BB plus. And so we can reduce to, so we had this definition of what an etalomorphism is. This one which is locally in a composition of open immersions and finite etalomorphisms. So well, there might also be rational embeddings if you like. And finite etalomorphisms. And then one can actually reduce to it being either a rational embedding or a finite etalomorphism. So even either rational embedding or finite etalomorphism. Okay. And so we have two cases to check. So we have the case where, let's call this map F, where F is in rational embedding.
Must be missing something. The maps from the A objects to the B objects are not Etal.
Sorry. It's a map down to the base. Considering.
Map down to the bases.
This,
Both this in this diagram.
both are more horizontal. Everything.
Ah, great.
Both of these maps are somehow as in this definition there is a.
Okay.
Yeah.
I was confused. Oh,
Yeah. Need some chalk. So if F is an open immersion in particular, then the homomorphisms into spar BB plus are a subset of the morphisms into AA plus, and it's just the condition that it factors over this open subset. So U embeds into spar AA plus. And so what you have to show is that spar A infinity plus to spar A plus factors over U implies that already this happens at a finite level. exists in I. But this is now a quasi-complexity argument. So topologically, this is just a direct limit of the spar AI plus. And so also
So you're using the fact that rational domains, you can wiggle the things that define them?
yes. So I guess you're referring to the statement. So it's easy to see that this bar is the same as for the direct limit without completing. And then there's a statement in general completing doesn't change this AX spectrum, which amounts to wiggling on the equations that define rational subsets. So if you take spar A infinity plus minus the preimage of U, and it's also the inverse limit of spar AI plus minus the preimage of V. And so the preimage of U is open certainly, so this thing here is closed in a spectral space. And so spectral itself. And so we assume that this here is empty. And so we have an inverse limit of spectral spaces which is empty, and this implies that one of them is empty. So why is this? So spectral implies that they are compact for the constructible topology. And so, which is generated by usual open subsets and complements of quasi-compact open subsets. All these maps are continuous for the constructible topology, so you have an inverse limit of compact spaces with continuous transition maps, which is empty, and so then one of them is empty.
So is this argument somehow the reason why you don't need the maps to be open anymore?
Yeah. Well, so the real reason I wanted eventually finite toss surjective transition maps in my PLD Koch theory paper is that later on in the paper I wanted to use some flatness properties, and those were only true in this case. Or at least I could only.
Because we're talking about perfectoids, nothing's going to be flat anyway.
Yeah, right. Okay. Yeah. There's nothing set here anyway, so I can just ignore that. Okay, so that deals with the. So I mean, like such quasi-complexity arguments always work when you work with spectral spaces. They work even better than for Werkowitz spaces, which you might think are a priori better for such arguments because they're really complex spaces. Okay, and so the second case is where F is finite état. And so recall from last time that.
Peter?
Yeah.
One question. So you were saying when you the fact that the limit defining the B is, I mean, at the very beginning when you reduce the case of the very first step, right?
Yes.
You mentioned that you use the uniformity at that step.
Yeah. So this is really representing. So the category of perfectoid tail rings really has all colimits, particular filtered colimits, and that's because you're always supposed to make the power bounded elements open and bounded. So you know what the power bounded elements in the direct limit are, and so you know the topology of the direct limit. So there's no choice you have, and but that's using this uniformity.
I see. But for example, is it clear that under continuous maps between these adic spaces that bounded sets always have to go into bounded sets, or is that not true?
Perfectoid rings, you mean?
For example,
Yes.
is this always true, the image of a bounded is bounded?
Yes. So if it's bounded, it's contained in.
No, because
No,
the
no, no,
target-
no,
the map might
no.
not be
If it's,
surjective.
if it's uniform. Sorry. In general? No, I'm confused.
Yeah,
At least if it's uniform, it's okay. No, in general, it's okay. So if it's a bounded subset, it's contained in some pi to the minus n times in ring of definition. That maps into some pi to the minus n
Oh,
times the
it's
other ring of
state,
definition.
sorry, it's okay.
It's state.
State.
Okay. So we're in the case where f is now finite et al. And so in this case, we want to use that that result of Elkig and Gabor-Romero essentially, that finite et al. A algebras as a category there is this fancy tool limit of finite et al. AI algebras. And so why does this? So this implies a result. Why? So the homomorphisms. Well, let me write an algebra. So we have to compute homomorphisms from B to A infinity. But that's the same thing as homomorphisms. So this is over A. But that's the same as homomorphisms over A infinity from B tensor A infinity to A infinity. But now this is a finite et al. A algebra, this is a finite et al. A algebra, infinity algebra. And so this means that this Helm space is the direct limit over all I of the homomorphisms over AI, from B tensor AI to AI. And then again we can rid of the space extension in the beginning. So it's a direct limit over homomorphisms over A from B to AI. And this is what we wanted to prove. So with all these topological kind of things, like even finite et al. Algebras, it doesn't matter that we pass to completion, and this means that we get such finitely presented more objects here essentially, because behaves as usual, usually finitely presented things. Okay, so once you know what morphisms between pro-état things look like locally, you can verify that pro-état maps have nice properties. Compositions are pro-état. Also, if you have such a diagram and G and H are pro-état, then F is pro-état. This is something that wasn't true with the definition I gave in my Pierre-de-Coq theory paper. Because this could be a point, this could be a point, and this could be a profinite set, and then this wouldn't be. That's my old definition. And then also pullbacks of pro-état morphisms are pro-état. And maybe I should recall that the category of perfectoid spaces has all limits. Along affine transition maps. Maybe I should write a phenoid. Some particular fiber products of perfectoid spaces exist. And so it's clear that the pullback exists, and then you just have to verify its Proiton, which is probably the easiest of the three properties. Okay, so
Can this property be checked Croitel locally? Is the property being Croitel local?
no, I mean, as an all paper for schemes, it's not, I guess. I mean, I didn't check that the counterexample of de Jong works as well for edX spaces, but
But there are some of it is a non-local Mendelian mass.
Could you speak more specifically to you?
so the question was whether you can check that the map is Proital
Yes,
locally.
yes.
And so you could ask a similar question for schemes, and on the target, which is probably a weaker statement than checking it on the source. And so in my paper with Bargev, we give de Jong gave us a counterexample that this is not true. But Bargev was just remarking that the counterexample relied on the same thing that you brought up, that local rings are not Henselian for schemes, but they are for these edX spaces. And so it's not a priori clear that the counterexample can be adapted to the setup, but I would expect it's not true. Okay. So using this, we can define some kind of big Proital site. So let me consider the category, let's call it perf. Perfectoid spaces, and actually just use the ones of characteristic P because that's what I will be doing in a second. So formally you might do a bit of stuff that's about to come, also if you use all perfectoid spaces, but let me already now make this restriction because I don't want to have two notations here. And so we endow it with the following structure as a side. By saying that a collection of maps Fi x to x over any index set I is a covering or a Proital cover. Right? If all the Fi's are Proital, and now it's not enough to say that X is covered by the images of the XI's. It's like in the faithfully flat topology, you have to be a bit more careful. In the FPQC topology. And so we make it S in the FPQC topology. So, and for all quasi-compact open U and X, there exists a finite set subset of the index category, and quasi-compact opens UI of Xi just in this finite index set, such that U is covered by the images of the UI over this index.
So this was the bit that was automatic with the old, with the weaker definition.
Yes, because maps are open, and then you can use quasi-complexity to get this. So. just saying. This bit of technicality is the same as for FPQC covers. Okay, and then that's a very nice site because we have finite limits and so on. So there is not much of an issue.
For a finite collection of points,
Yeah,
you would not allow as a Proitel cover.
yeah.
The Proitel cover is coming from each point. that you-
Yes, right.
Yeah.
That's a very good example. So if you have a profinite set over a geometric point somewhere as a space, then you could cover it by all the points individually. All the maps are Proitel, but this is not allowed as a cover. Okay, so what's even better about the situation is that this site is really subcanonical. So
But actually, I somehow am worried that you can't take this protocol locally.
well, I mean, so anything that's somehow only Proitel, I mean, somehow. I mean, if you define a site, you don't have to a priori ensure that all the coverings, if something is a covering after a cover, then it's a covering. I mean, you can just somehow formally adjoin it afterwards. Doesn't matter.
See how he uses it.
What?
See how he uses it. Could you say this is sort of technology generated by open
Yeah, so it-
subsets and at once?
I could say it's a topology generated by open subsets and maps of the form on affinities I was writing down such that the total map is surjective.
It's a single map or?
Well, finitely many
Yeah,
together.
okay, yeah.
Okay, so for a perfectoid space of X, and okay, because I'm using this generality in characteristic P, it's of characteristic P, but it would work if I allowed all perfectoid spaces, it would work the same. You have this functor represented by X, which sends any Y to homomorphisms from Y to X. And so that guy is a sheaf on the Proitel side. And so the essential point is just to show that the structure sheaf X maps to X of X, that this guy is a sheaf of the Proitel topology. And so, so it's certainly a sheaf for open covers, and so we have to check for the other kind of coverings that occur, which are often attenuated by finitely many attenuates in the standard way. So without loss of generalities, is X, say spar R plus factoid attenuate. And let's fix pi in R plus a pseudo-uniformizer, which will automatically divide, this piece power will divide P because of the characteristic P. And so say this has a finite cover by xi's. You can also make a phenoid R infinity I. R infinity I plus, where each R infinity I, R infinity I plus, is a completed direct limit of things over some index set. And then complete. The index set depends on I, but I guess I could make it independent of I because there are only finitely many. But let me pretend there was just one index set.
So you say the eyes are finite.
Is there only finite cover? Yeah. And so let me make a finite claim. So let me explain claim that if I look at the sequence of these plus algebras mod pi, and then I could also use intersections, and I don't want to introduce notation for that, but this long exact sequence for this kind of covering is almost exact. Meaning that all cohomology groups are killed by all fractional powers of pi.
The whole thing, the whole complex.
The whole complex. So this would even mean that I simultaneously am proving that all higher cohomology on affinoids of this OX on the Proitos side vanish. Why is this? So let's first look at the sequence for any individual j. And so there we get that the sequence of R plus mod pi, the product of the R j plus mod pi, ji over I, and so on. This is almost exact. That's because the higher cohomology on the étal side. So all of these are now étal. And we know that for affinoids, the higher cohomology of OX plus is almost mod pi. It's R plus mod pi. I 0, and 0 if I is bigger than 0, at least almost. And so now we can take a direct limit over all j. And then, because we're working mod pi, we really get the sequence for the infinities and don't have to complete. So, and the direct limit, filter direct limit of almost exact sequence is still almost exact. But at this point, it's really crucial that we know these sequences are almost exact and not up to some probably bounded torsion. Because this bounded torsion might a priori grow as we go up. But if it's always almost 0, then there's no issue. Okay, and so now we can just pass.
Can you briefly say what, I mean, just given that there were like no real finiteness hypotheses on the things there, why the handling the structure sheet?
What was the question? Why is this the essential point?
Come to that later. I think you should finish this argument first.
Yeah, let me finish the argument first and then.
Oh.
Um, because these things are all flat, all terms are flat and p-adically complete. Pi torsion free. And pi.
Is this some sort of inverse limit there?
Yeah, so I mean,
Careful.
mod each power of pi, this is, the complex you get is filtered by, I mean, the individual complex is mod pi. All of those are almost exact, and then you take them together. It's still almost exact. And then you take an inverse limit. But that's exact in this case, because all these terms are...
Exact, be careful. It's probably okay because there's a bit of that Leffler condition you have to check, but
All these terms are like as simple as they can be if you take inverse limits.
kernels and co-kernels too, no?
No, there are no kernels and co-kernels. Everything is pi torsion free.
Maybe.
Like if I do it in the almost world, it's really like an exact complex, and all terms are complete and pi torsion free and so on. And so then you invert pi and get the result. So the result of this thing of the essential point. And so I want to check it's a sheaf. I can, like it's clearly, this is a sheaf for the usual site given by open subsets, and so I can reduce to the affinoid case. And then I have some cover. And because X itself is a quasi-compact open, I can reduce to the case where there are only finitely many I, by this assumption, by this definition of cover, and the Xi are quasi-compact. But then each Xi admits a covering by affinoid open subsets, which have the standard form. And so, as all of them are quasi-compact, finitely many suffice. So, all Xi are some space A infinity plus. There's a definition of Proital maps. And so, sorry, what am I doing? I want to cover the Y. Sorry. And and so what you want to produce is a map from R to S, and so we get a map from R to the H0 on Y Proital for Y. Because after a Proital cover, we have a section. We have maps from R to S infinity, these S infinity I's, which do agree on overlaps. So we get such a map to the H0 here, but we just showed that this is a sheaf, and so that's Y, and so we get the desired map. Sorry.
Use some strictness condition as well to control the continuity. Oh, everything is taped.
Yeah. I mean, so if you want, this is even, it's not just a sheaf, but it's a sheaf of topological rings, as follows from the argument.
Could you explain again how we get this statement of the proposition that was completely wrong?
Okay, so by using that everything is a sheaf on the usual, for usual open coverings, you will first reduce to the case where X and Y are affinoid.
Yes.
And then what I want to check is that if I have after a Proital covering of Y such a map which agrees on overlaps, then actually it comes from a map from Y to X. And so I chose this covering of the yi to y there, over which I have this map. And then by definition of covering, because Y is quasi-compact, I can assume that there are only finitely many terms in the covering, and that all the yi's are quasi-compact. And then locally they are of this form, and by quasi-compacity I can assume they are all of this form, where they are affinoid and some are. Well, I guess I was somehow reducing to the situation I was using there. All these maps are in the essence definition of Proital maps, so an inverse limit of Étale things. And then this argument I gave there produces you a map from R to S.
I guess he never wrote down the map from R to X.
Yeah, so yi to x corresponds to a map from RR plus to S infinity I, S infinity I plus. And they agree on overlaps. And so this means that with R replaced by S, you can now get a map into here, or which agrees so here, and so it factors through that term there. Okay, so this means the situation is much better than when I try to abstractly define some nonsense. But now I want to again define my diamonds as some kind of functors of points for this Proital side of perfectoid spaces. And so I say that the map F to G of sheaves, this category perf, that such a map is Proital. If space is X and maps Hx to G, which correspond to sections G of X. If you take the pullback of this map, Hx times Fg times Gf, this is representable perfectoid space. Y. And the associated map y to x corresponding to the map from hy to this Proital. And now at this point, Arthur's comment is correct that because I can't glue Proital maps Proital locally, this might be a bad definition. So, oops. So I think I should add that this is possibly after Proital localization on X.
Including the representability or just the Proital?
Well, maybe actually both, yes. So it's also not clear that you can glue perfectoid spaces over Proital covers. Although this might actually be true. On perf, I said there exists a Proital. There exist Proital maps. From representable guys, such that together they're surjective.
Now the equivalence relation, so to speak, only has a kind of representable Proital covers.
Yes.
Is index set arbitrary?
Yes, the index set is arbitrary.
Okay, so there you go. You don't need kind of.
But I mean, surjectivity somehow means that any section can be somehow lifted Proital locally, and there is quasi-compacity is built into this, what it means Proital locally to be the image.
There's no finiteness condition on the diagonal either.
No finiteness condition on the diagonal, yeah.
But so you don't need a condition like in the definition of cover of a Proital cover.
No, that's what I was trying to say. I don't have such a condition here because I think it's already built in the surjectivity here.
Oh, because of the definition of the cover we made earlier.
Yeah.
So can I ask, sort of in the spirit of Grothendieck's poetic vision, why do you call them diamonds? What,
Yeah.
how is that?
So because in whatever way you look at them, you see like can only look at them from something perfectoid, and so somehow you see profiling many times the same things in some sense. Right?
Is the idea that you have like the top of the diamond and you don't literally have the object on the bottom?
No, I mean
Maybe it is a very.
Like if you look at a diamond, you see many times the same thing, and so because of all these reflections, and so like whenever you look at it, you see how profiled many times the same thing because you can only look at through these Poisson maps onto
You
it.
think of all the facets of the diamond, it's hard to see it.
It's like a hole.
All the facets of the diamond give you different ways of seeing it. The facets of the diamond you're referring to.
No, like
Well, when you look through, it's
when you look through it, somewhere you see like.
you get the reflection.
And also there's a Tesh symbol / diamond. Well, backslash diamond. So let me introduce some notation. So if R plus is perfectoid, I somehow say if it's of characteristic P, I have the associated perfectoid space bar R plus, and this gives me a representable object, which in particular is a diamond. And so I want to use some new notation for this, and so I write. I mean, again, writing spar would be bad, and so I'm writing spar D, where D stands for diamond, for the object represented by the adic spectrum of the tilt. So tilting is now built into here. It's not already of characteristic P. And actually, this functor will be extended to more general Huber pairs later.
It's in the category of diamonds.
Yeah, so this has a diamond.
Are diamonds really hard?
Well, they're in some sense very rigid objects. Yeah? So like if you have a perfect complex, its cotangent complex is always 0, so it's extremely rigid. And also it's somehow in the same word as crystals. So. I don't know. So we have a fully faithful functor X maps to X diamond from perfectoid space of characteristic P. So X diamond is then just a functor represented by X. And so, for the rest of my lecture, I wanted to discuss an example. I mean, the example I was already mentioning at the beginning of my lecture of a diamond. So, the spar diamond of QP, according to this more general definition I didn't give, I defined to be the following. So, just expand the notation here. It's the diamond for the cyclotomic extension modulo the action of CP cross. And so, yet more precisely, it's a diamond represented by this perfect power series ring. Cross.
So we're going to see later that this is actually the spot of QP-ZP according to the general definition.
Yes, yes, yeah. Where QP is cyclotomic. Um, so what is a functor actually? So say if x is the spar g of RR plus, where R is perfected of characteristic P. What are the R points or the X points of this thing? Well, the first thing you can do is you can pull back this CP cross cover here, and we'll give you a CP cross cover of R. So it was R to R tilde and CP cross torsor. Equivalently, it's a completed direct limit of C mod P to the n cross torsors, where these are infinite Étale extensions with this gamma group. So. R n where R n over R infinite Étale with gamma group. Plus a ZP cross equivariant map.
Just R to R tilde is a ZP star torsor, is that what you're saying, or rather?
Yes.
Spec.
So I'm giving a definition of what I mean by ZP star torsor. And a ZP cross equivariant map to R tilde. And that stuff up to the office. And so what is the second datum? It's a topologically nilpotent element T in R tilde, which is the image of this T in here under this identification, topologically nilpotent unit T. And the Galois equivariance means that for all gamma and ZP cross, if you apply gamma to this element T as an element in R tilde, it's supposed to be this formula for the action of gamma of ZP cross on this field here, which you get by functoriality from the action here. And you can make this explicit, it's this action.
So this is the thing that we imagine is the descent datum, even if there's no descent at all.
Right. Right. So we would like to say that this gives us a map from the invariants in here to R itself, but there are no invariants, and so yeah. And so you're looking unhappy.
Just very fast.
Sorry, is the action like fixed point free in some sense?
Yes, so the action of ZP cross on the tilt, on this thing here, is free. So there are actually no automorphisms when you form this quotient here.
So this remark presumably to be proved.
Yes.
And we have the definition, so.
Yeah.
I mean, literally, you get a covering of X. I mean, section of,
Yeah, but I mean, this covering of X is equal to this map.
what if you get some exotic covering and data on each one, open it, you can really glue to get an actual torso.
So you have a surjection. Sorry.
Because X tilde is a priori just not like an honest space.
Yeah, it's a diamond.
Um,
Or because
But-
ZP is also
so what does it mean to give such a covering? So to give, so it's by definition a pure Tolschification. So there exists a cover fi from some xi to x, which we can assume to be of standard form. So this is some spar r infinity I. Infinity I plus with some spar I plus. As in the definition of Proital map. Okay. And we also have maps from now this QP cyclotomic guy to there. So they correspond to some elements Ti, topologically important units. Such that over a complete tensor product there exists some gamma and ZP cross, gamma and J. With gamma of Ti tensor 1. Am I getting this right? Yes. This one tensor Tj. Gamma ij. plus a co-cycle condition.
And gamma ij knows how to operate on Ti, sure. So maybe it might be a Ti then tensor 1?
Ah.
Tensor 1.
So now I want to shit.
I like that parenthesis.
I'm going to prove some general lemma that like a ZP star, pro-étal ZP star torsor over an affinoid is not always given by an affinoid by building up from finite étal guys using this Kedlaya loop.
Yes.
If there were only one Fi, would you be in better shape?
I can assume there's only one, yeah. I mean, I can just take the disjoint union. That's okay. No. Okay. Yeah. So what I should try to do is build these RNs, each one of them. And so I should try to build some finite étal cover of the base. And so it should be possible to define this finite étal cover over each R infinity I just by inspection, because there I have this map. And this should come with some descent datum on the pro-étal side. So what I have to show is that I can descend finite étal covers along pro-étal covers. But everything which is finite étal cover on some pro-étal thing, it already comes from some finite level. And everything is finitely presented, and so this finite étal thing should already get an étal descent datum. And then the étal descent datum, one can show that one can descend finite étal covers by approximation from the Noetherian case eventually. So this produces the SRNs. And hence the R tilde. And then I have to show that I actually get a map into this R tilde there. But then over this cover, I should have adapted the co-cycle so that it really, all the elements are the same locally, and so I really get an element downstairs. I admit that's a bit much.
12 days to digest it.
The theorem I wanted to state.
But it should be true that if I give you a ZP star torsor for the pro-étal side over an affinoid, it should be represented by an affinoid, right?
Yeah, right. So what I have to prove, and that was the argument for this.
Yeah.
Yes. So next lecture. Anyway, so let me just say that this way one can prove, well, the theorem I wanted to state is the following, that if the category of perfectoid spaces over QP is equivalent to perfectoid spaces X of characteristic P plus a structure morphism.
So you need to find perfectoid spaces over non-perfectoid field.
Well, it's just a perfectoid space together with a structure morphism as Edding spaces to QP. Together with a structure morphism from this guy to the diamond associated with QP in the category of diamonds. So this makes precise what I stated last time. And I had prepared a proof of this using that definition of what spar D of QP is, but time's up.